So, hello, welcome back. So, this video would be writing the continuity equation for an infinitesimal fluid element. Our last equation was for the control volume for a bulk nature of fluid, but now it's for looking through the bulk. We break the bulks into fluid elements. So here we have a bulk of fluid. This will be like flowing water in a pipe or a pond, pipe or pump, whatever it is. So we want to look at the properties of the fluid by looking at the properties of individual fluid elements. And so these elements are like cubes. We call them delta V, volume D delta V. And then in this fluid, the flow properties are constant, so they don't change. So we could think of like the fluid as being made up of each of these blocks, each. And then as these blocks, each of them move, we find the properties change, in general, change. And this changes according to the normal rules we want to talk about. And then the flow of the fluid can be seen as an aggregate of the flow of each particle. So let's get started. And I wrote here we'll be using this a lot, the divergence of the velocity. This is a mathematical operation taking divergence of velocity, but it also has in the fluid dynamics, it has a lot of physical. He has a physical interpretation that I would love us to appreciate, because we'll be doing lots of this when we get on with more derivations. So let's us look at divergence of the velocity. Divergence of velocity. So the divergence operator we know from vector calculus is the divergence operator, which is del dot, can be written as this: d dx plus d dy plus d z. So basically it takes in a vector operation. So let's say the a, which is a vector, it takes ax, then ay, and then az. Physically, in normal math operator, we see the divergence operator as a source or sink operation. So locally, at any point where the divergence is non-zero, we can see that there's actually a source or a sink coming out from that point, because the divergence means like a coming out, like a creation of stuff. And wherever there is no creation, the divergence is zero. So this is a source, this is a sink. They're really beautiful math identities. So we'll see what it means here. So for the measure of velocity, let's start with the fluid element, our known control volume. But the control volume now, let's make it move in general with a velocity v. So control volume v, it moves with a velocity v. So not in general moves with a velocity v, the whole thing moves, but let us single out a patch of area that moves with the velocity v. And these are a part of area will be ds with a normal coming out in this direction and come out in any direction. But the normal is always perpendicular to the surface. So then this moves with what? A velocity v. So meaning that in a small infinitesimal time delta t, in time delta t, this area moves a distance v delta t. So that means in time delta t, ds sweeps out a cylinder of volume v delta t. This is the speed, you know, volume is base times height, base area times height. So this is the height, then the base area is ds. Now it sweeps out the volume. The area of a prismatic surface is actually perpendicular height times volume. So we have to see that the v and the ds and their vectors have to be lined up parallel to each other for you to actually think of a volume. So in essence, the volume of such a what do you call it, such a cylinder spread out is actually the dot product. So it is what? V dt dot ds. Now this is for just this element of area. Now for any other element of area here, it will have its associated velocity and volume being swept out. So, and that, if you think of it, that is how the control volume deforms as it moves. Each area moves and then sweeps out cylinder. So the change in volume is actually total change in volume. Total change in volume. Total delta V is actually the area integral of this product here. Now, we use our divergence theorem again, which tells us that this is equivalent to what? The divergence V delta T dV. So now that being said, we can see that this statement here, the V is equal to V now I promise to make distinctions between V for volume and V for velocity. It's kind of getting real difficult. That is one very difficult thing to have in fluid mechanics. Velocity and volume. Maybe from next videos, I'll choose another naming conventions for this. So now that we have this, we are going to divide both sides by delta t. So dividing both sides by delta t, we have the v, the t is equal to triple integral of v 1 over delta t now for a fluid parcel, which I told you an infinitesimal fluid parcel, such quantities are usually constant throughout the control volume and can be brought out. So this gives us 1 over delta t divergence of v delta t, and then the integral alone gives you what? dv. So now, for a short amount of time, a short step in time, this can be written as the exact derivative, which is dv, the dv dt, that's the total derivative, is equal to this cancels, and then we have divergence of v times the volume element. This implies that what the divergence of v in a fluid parcel is equal to 1 over dv del. Now dv, we were using a small fluid particle. That's what we will use because we're talking about small fluid elements, the t. So this is the interpretation for the divergence in fluid dynamics. It's something that really helps once you keep it in your mind. Divergence could give you an idea of compressibility of the flow. But in general, the divergence of the velocity gives you an idea of the time rate of change of volume per unit volume. So for fluid parcel, whatever it is, we want to check the time rate of change of volume. How fast does it change per unit volume? That is divided by the original volume. That gives you a rough idea of what the divergence of the velocity means. So that being said, let us move. We still have, so this being said, the other derivations or the second derivation of the continuity equation now can be done. So given mass conservation, for our fluid elements, we name this the infinitesimal fluid element. It can be found to be equal to rho del V. Then the change in mass as it moves can be seen to be change in mass as it moves can be seen to be d dm dt. This is seriously, the capital D are called substantial derivatives, total derivatives, which is equal to the time. Let me write it here. Let me look for some space to write it. I should have introduced that concept for the start. D dt is equal to d over dt plus v dot grad. So this gives you the local change plus the convective change, which is the total change. So d dn dt. And now if we differentiate this, this is d rho del v dt using our product rule, rho del v dt plus del v the rho dt. Now we can divide both sides by this is equal to 0. Divide through by del v divided by del v. We have rho 1 over del v 0 v dt plus the rho dt equal to 0. However, this we found earlier to be equal to the divergence of the velocity. Therefore, we can write that what rho divergence of velocity plus the rho dt is equal to 0. Yep. You could see that for moving them to opposite sides, the rho dt plus rho del v is equal to 0. So this is also the continuity equation written in the form of a moving fluid element, and we could show it to be equal to the first form which I showed in the first video, which is very clear. So go to new section. This was the rho dt plus rho del v is equal to 0. And the other one was the rho dt plus equals to 0. Now we have to remember that for the material derivative, this is the rho, the t plus what? V dot grad rho plus what? Rho, the v is equal to 0. But if we look towards the vector identity, the divergence of a scalar multiplied by a vector is equal to rho div v plus v dot grad rho. So they're equivalent. So that's just the essence of the continuity equation. Matter can be created, not destroyed. Wherever you have the change of mass in a moving fluid is always due to the inflow and outflow of fluid. There was no mass created inside. Whether the fluid is compressible or not. So you could see that this also works for compressible as well as incompressible fluids. For incompressible fluids, we would look towards this. For an incompressible fluid, here we have that the local change in density is always 0. The local change or the total change of the fluid is always 0. So if the rho the t is 0, we have here that what? Del rho v is equal to 0. But rho is constant throughout, so you could bring out rho. You can bring out this identity to give you this. Rho into what? Grad v plus v dot grad rho is equal to 0. But rho has been seen to be constant, so this is 0. There's no gradient in density. So we have what? Del v, the divergence of velocity must be 0, which is also affirming what we interpreted as a divergence of velocity, which was the change in volume per unit volume, which also gives the idea of compressibility. So from here, we would move into the Navier-Stokes equation, which is basically the statement of F equals ma written for fluid elements, for fluids. So stay tuned. Thank you for